right side you can see that.
Oh, here you cannot see. So they will chat there.
Yeah, they will put their questions in the chat.
They will see us and put these things on
Yeah.
the chat. Here the chat will not work.
No.
Okay.
Is there some issue with this because sometimes it works. Okay.
How many are there?
Around 470.
No.
Oh.
Who have joined? Can you see how many have joined? Hello everyone. How many of you joined? Can put your questions on the chat. There were no questions on the portal, right?
No, there was one question. I mean, one student was asking about clarification in the factor group. Maybe we can start with it.
But can anybody be there or can?
I can see.
Nobody is there?
Four watching now. 4 are here.
Okay. Hello everyone. If you have any specific questions, you can put it up on the chat box and we'll take it up. Otherwise, there was some question about factor group. That's what Leika, who's the TA, is saying. Who are watching now? Who are the two? You and me. Unless we start typing, you won't know who's putting in a message. Okay, so let me start with the factor group. This one? This will work? Let's see. So typically a group you can have, and then you can have a subgroup, right? And this subgroup is called as a normal subgroup or invariant subgroup if G inverse HI G is an element of H, then it is a normal subgroup. Correct me if I am wrong, Lekha. Yeah, or it is also called as an invariance. Okay. And interestingly, if you have an invariant subgroup, you can construct left coset and right coset. And left coset will be equal to the right coset. And you can define G mod H. And this is what we call it as a factor. And this factor is also a group if H is invariant. Okay. Okay, so this is what is the definition. I probably have discussed this. Let me change the. I probably have discussed this for some simple groups like, permutation, symmetry group of degree 3 or something, which is also isomorphic to C3. Have I discussed this already or not yet?
We have discussed it. Yeah.
Okay. So here you can have an invariant subgroup, which will be, if you take it to be a C3, is an invariant subgroup. and you can form the factor group, which is nothing but the sigma v. Okay, so you can show that this over, in this case you can define the symmetric group, you can define alternating group of degree 3, which is a cyclic group with 3 elements. That's why this is isomorphic to this. And you can define this to be the factor group, and that factor group is just, I think, an element identity and a 1-2 element in the language of transposition element. And in the context of this, you can write it as E and sigma. Okay. So that will be the factor group. Okay. So this is the factor group. Am I right? Yeah. So any questions on this? Maybe you can type it out there and then we could answer this. If you have any queries, you can ask me. Was this a specific query, or if they had anything more in this factor group?
No, actually there was a question from the video, so I answered that, but I thought it is good to start with the definition.
Yeah, I think probably in the video there's some, I probably mistook E. See, interestingly, if you do a factor group with E and 1-2, that is also turning out to be a subgroup, which is not the case in general. In general, the factoring should be done only by an invariant subgroup. Okay. If you do it by the other group, you may not get that factor to be a group. Factor will be not satisfying the group level. Accidentally it happened that in the lectures, when I took O3 and E and 1-2, it gave me again an A3, which is a group.
Right.
But that will not happen. So in general, you should always do a G divided by an invariant subgroup.
Right.
And that will always give you a factor group.
Correct.
Otherwise you will not get. Some accidents can happen. G by an arbitrary subgroup could give you a factor which is also a group, which is what happened in the lecture. But that is not the, it's not the definition. The definition is invariant subgroup and group, and then you have to take the factor of G divided by the invariant subgroup, and then you can show that it is a factor. I hope this clarifies the discussion. Yeah. You can check whether Vishal, are there internship opportunities available under you for the top scorers of the school, as I wish to work on knot invariance and quantum gravity later on in my PhD. Wow. Okay. So I will put in a request. I think I can put in this summer. Most probably I'll be there from June. I think for 6 weeks or something, I will ask the NPTEL whether such an opportunity is possible, Vishal. Okay. Whoever is topping the course, I think the top scorers, how many they will assign, NPTEL and all, I have to figure it out. I'll talk to them and I will update it on the portal maybe a week from now. Okay. Yeah. What else? Any pertinent questions based on the videos, or any doubts, any more clarification? The live sessions are mainly for, if you have an one-to-one questions to ask, I'm present here for this 1 hour, you can ask me and I can clarify your questions. Please let me know. How did you change? Change. So till 4 weeks are over, no? Or how many weeks are over?
So it started in January. Yeah, I think around
3 weeks are over.
Yes.
So they've started, they've finished the, they've not yet started character table.
Character table.
Great orthogonality theorem, character table is started.
I accidentally stopped showing.
No problem. It's okay. We'll do it again. I don't see anybody typing or Unless they have questions, I don't want to take a lecture here. Only Vishal is watching me. What are the topic you think they've asked any questions which I could discuss besides the fact
Yeah,
of
so there were 3-4 questions on the same topic. So students were struggling with the multiplication of that symmetric group. I mean that they are applying some permutation. So they were getting confused. So I tried answering them. I don't know whether they get clarified or not.
What happened? This is not even open or? Okay.
Oh, but I think the screen has not been shared yet.
I shared it, right? Yeah. Okay. Okay, so typically whenever you have a discrete group, you have to define besides the identity element generators. Okay. Once you have the generators, you start building up the group elements. And for this permutation group or symmetric group of degree 3, you can have problem. Close. So degree 3, you know that this has how many elements? 3 factorial elements, which is 6 elements, right? So identity is one element. You can do an exchange of one and the second object. That's one transposition. Then you can have 1 and 3. You can have 2 and 3. These are the possible. You could multiply any of the 2 and see what you get, and you can get a 3 cycle is what I would have defined as 1 3 2 or 1 2 3. You can first take the 1 3 and then multiply, so you can get a 1 3 2. So these are the 2. So this accounts for you the 6 elements. Okay. So using these 6 elements, you should verify which one belongs to the conjugacy class. Okay. Anything with the same striker structure most probably will be in the conjugacy class, but you have to check it. In this case, it turns out that this belongs to one conjugacy class, and similarly these two will belong to another conjugacy class. So there are actually 3 conjugacy classes. Okay, so you can multiply 1 2 with 1 3 and see whether you get an element in this set itself. So then all the properties, the group axioms are all satisfied. And this is the shorthand notation of looking at this group, symmetric group of degree 3, where there are 3 objects, 1, 2 and 3 are the 3 objects, and you allow transposition or permutation of the 3 elements, and you should end up getting the group elements of that group, which are 6 elements. Is that okay? If you have any specific question, if you put it on the chat, then I will know what exactly you have a problem and I can explain it. Until you tell me, I will not know what exactly you are looking for. Okay. Next page here, huh? Here, this one. A lot of interesting thing happens with this symmetric group of higher degrees. Okay, suppose you look at symmetric group of, let's say, 7 or symmetric group of 8. You know, the number of elements is 7 factorial, number of elements here is 8 factorial. And then you can construct subgroups in this 8 factorial. There's a lot of interesting developments here. They call it as a monster group and so on. So very interesting. You know, if anybody is interested, you can start looking at these, which are all subgroups of the symmetric group of degree 8 or higher degrees. How to play around with the tools which I have taught for a simplest example can be applied to many higher degree symmetric groups. Okay. What else? We need to practice by doing those point groups, stereographic projection. From the stereographic projection, you can actually see which belongs to the same conjugacy class, right? So the point groups which are catalogued in the literature are cyclic group with Cn with vertical mirror symmetry. You can have Cn with horizontal mirror symmetry. You can also have dihedral groups, dihedral with horizontal and so on, right? And there are higher things like this tetrahedral symmetry, octahedral symmetry. And for each of them you can start writing down the set of elements and then grouping them into conjugacy classes, determining how many conjugacy classes are there. Right? So you can do many with the basic formal definitions and formal simple examples. You can start looking at it for these cases. There are also some groups which you can rewrite it as a, the CNH, you can write it as CN cross a sigma H. Sometimes this is called as a direct product group. Whereas CNV, I cannot do that. This is not a direct product group. It is CNH is a direct product group, but there could be a semi-direct product group. Okay. So it's very interesting. If you start looking at it systematically, the tabulations of all the point groups, what are the generators, what are the conjugacy class, whether it is a semi-direct product or it's a direct product, can all be checked. Okay. So whatever you're doing it for discrete groups, later on can also be generalized when you have many elements, which is, large. Discrete can be there if you take the degree of your symmetric group to be large, but you can also have something called as a continuous groups. Rotation by an infinitesimal angle, and that angle Each one will be an element, but then the number of elements will be huge and infinite and parameterized by a continuous parameter, which is the angle of rotation. Okay, so you will see that towards the last 3-4 weeks, you will see the continuous groups also. Discrete group seems to be playing a very important role lately, even in the context of neutrinos. The 3 neutrinos which once upon a time were treated to be massless are no longer considered to be massless. They seem to be oscillations, neutrino oscillations, and then this 3 neutrinos, which are called electron neutrino, muon neutrino and tauan neutrino, can be systematically made to rotate by a discrete group, which is an alternating group of degree 4. You can do that and look at this as a way in which you can study, exploit properties of them in physics. Okay. Anybody is interested can take a look at it. But the tools which you learn in this course is really useful. Later on, when you go for advanced topics, applications in physics, you will start seeing that these tools are the main essential foundational tools to help you to focus on fixing the terms in the Lagrangian, fixing the terms in the Hamiltonian, which respects that symmetry. How do you fix it? What else? Was this announced well in advance for all the participants?
Yeah, I myself sent one mail in the discussion group that there will be a live session.
Okay.
If there is any questions, then you can ask.
Not many people have come. Probably it's clear enough in the lectures that they don't have any queries.
Yeah, maybe.
Or they see the recording. If there are no further questions, maybe we can stop the live session. Maybe we'll wait for 5 more minutes and stop it. If you have any specific thing, you can ask me. Stereographic projections and all is clear enough. Multiplication table, that's the main thing. We are watching now. If you have any specific question, please put it on chat, then we'll know. Can you all hear me? If you cannot, if you can hear me, put a thumbs up or something, then I will know. If you have anything specific which was not clear in the lecture, you can ask me. Live sessions are meant to clarify your doubts one-to-one. Please let me know. what is the order of a direct product group? If you are given a G1 and a G2, G1 let's say has order, let's say the order of that group is N1 and G2 order of the group is N2. The direct product group G1 cross G2 will have, what will be the order of that group? Do you know? What will be the order? Now I am doing the lectures.
If you want to stop, you can stop.
Yeah, so I'm just checking whether they will all write something. 3 people are watching. So I'm hoping somebody will write, otherwise they will stop. Okay. So you can check the order of this group. What is the order of this group? What will it be? The order of G1 is N1 and G2 is N2. What will the order of this group be? Will it be N1, N2 or N1 plus N2? Check this for C3H. What is the order of the group? Or even C4H. What is the order of C4V? You can check and see whether it is a direct product group or it is not a direct product group. Okay? Yeah, everybody is probably tired. They're not even typing anything. Maybe they are probably listening to me. But unless they type or say something, I won't know whether they are really listening or watching. Okay, if there is no further typing or anything happening, I'll assume that you have understood the last 3 weeks of lectures and you are into the 4th week. And of course, you can put your questions on the portal and TA Lahika might answer. She can answer or I can also answer.
Example could be a factor 8 times.
GS is some name. Okay.
Yeah.
In the factor group example could be factored it by H2 star E union H2 star AB instead of H2 star H2 squared union H2, yeah, so that is up to you. You can always take in the factor group in the coset, you know, when you take the coset you can look at it as E and A or E and AB, you know, that's up to you. Okay. But it will be one candidate of that coset, can't be okay. You can construct the cosets, right? The left coset or the right coset. Is that right? So for the invariant subgroup 3, you can have every coset element which you are writing can be one of the candidates from the three coset elements. Am I right? So let's take that C3b example. Right? You had identity and you had a coset, the subgroup which was 1b and b squared, right? So this was the subgroup. So let me write this. This is the invariant sub. Okay? Am I right, Leika? And then C3b is generated by generators A and B. Okay. First coset can be obtained by just multiplying identity with 1b squared. Okay. So that's trivially the invariant subgroup itself. This is one coset. The second coset can be A multiplying 1b squared. Right? B multiplying something has no meaning. It gives you itself. Right? If you multiply b, the b will come here, then b squared, and then b cube as identity. So you don't get anything. So these are the only two cosets possible. Okay. You could have done this. I did it by multiplying the element with the subgroup on the right. You could also do the subgroup on the left and the element. Okay. So, but in the context of invariant subgroup, this whole set which you get, this will be three elements, right? 1, b and b squared. Okay. And similarly this one will be a, ab and b squared. So the question which you are asking is, can I take the union? Yeah, ab squared. Okay. So you know that E and A forms a order 2 subgroup, right? What about E and AB? E and AB? Someone? A squared, B squared, right? A squared is identity. So E and AP doesn't form a, but you can always take the subgroup multiplied with AB. Okay. If you do that, instead of A, your question is, can I do it with AB? Is that what you are asking? Provided E and AB forms a subgroup. That's not happening here, right? Because if you take AB with AB, probably it's true. Maybe you can check. AB, AB, and BA is AB squared. There is a property, no? BA is, what are the properties? A squared is identity, B cube is identity, AB is BA squared or B squared A?
BAB is
B squared A. Right?
yeah.
AB is B squared A.
Yeah, that's correct. BAB is A, so AB is B square, correct.
Correct? So you have to use that fact that AB is B squared A, right? And then this is identity, and that is identity. So this is also an order to subgroup. So you can use any of these to write your union. Okay? You can take any of these candidates from the coset group to write the union element. It's allowed. So here I took A and E to write the union of the two groups with the subgroup, invariant subgroup, which is this. But you can take E and AB, which is also, this is another candidate in that coset group. That's also going to be an allowed union, which is giving you the same group. So you're not getting anything, but it is, you can't call it not unique, because this is just one single choice I made, but you could have multiplied this with this and taken that choice also. So it's allowed. Okay. Is that clear? So always give you that group. Any candidate of the coset, if you take an union of them, you will get the same group. Not any specific choice. But you have to apply these properties. Because at hindsight, initially I thought that this one is not an order to group, subgroup, but actually it is an order to subgroup. Okay? Yeah. Anything else? Okay, if there are no further questions, I think I will sign out now. And regarding this internship thing, I will check it out with NPTEL and I will send out an email in that portal. I'll request Laika, I'll forward it to you. You can just post it on the portal. If you have any questions, any doubts or any mistakes, if there is any typo in the assignments, there is some error, you please point it out. We'll take a relook at it and we'll re-evaluate. And of course, participating in the live session will help. I see very few people are participating. In spite of announcing well in advance, probably people are not free at this time. If you have any specific convenient time where you will all be finding it convenient, you can also inform us on the portal. Next month when we have a live session, we could try to make sure that majority of the students' convenience is taken care of when we offer the live session. Okay? Okay then. So then we will sign out now and see you next month. Bye bye.